My name is Ania Wielgopolan. I work in Institute of Geophysics, Polish Academy of Sciences. And today we're going to talk about weather, but it's a very special kind of weather, space weather, and what it is, why it happens, what are the consequences of it, and what are the conditions that influence space weather. So we're kind of used to weather forecasting, but normal weather forecasting, more or less accurate regarding what's going to happen tomorrow or maybe in a week, like in terms of temperature, precipitation, clouds, and so on. But actually, there is a special kind of weather that we should also consider because it's very, very important. It is also observed, even though many of us don't know it. There are also weather forecasts for space weather, and why we should be interested in that, because it influences and may influence even more our reality, our everyday life, and possibly could pose a danger much worse than a hurricane or tornado, those normal weather phenomena, we might say. But those space weather phenomena can be much more dangerous on a global scale. So it all begins with the sun. The surface of the sun is a very, very busy place, even though we cannot see it with our bare eyes. It has electrically charged gases that generate areas of powerful magnetic forces on its surface. So these areas are called magnetic fields, and those gases are constantly moving. And because they are moving, they're stretching, twisting those magnetic fields, and this motion of gases, those changes in magnetic fields create a lot of activity on sun's surface, and this activity is called solar activity. And this solar activity influences the whole solar system, and even though we are very, very far away from the sun, it doesn't seem so far away on this image, but of course we need to have the scale in mind. So this influences Earth in many, many ways. Also, you need to remember that not only Earth rotates, Sun also rotates, just like Earth, which will be actually quite important for space weather, and I will mention it later. So what is space weather? So we have the sun. It plays a large role in providing the Earth with what we know best, like light and heat, all those that allow all those processes, allow life on our planet. But there are actually more subtle effects on Earth, but also on Earth's weather, on Earth's climate and atmospheric processes that are still actually a mystery to science. So scientists are especially puzzled by some of these phenomena, like solar wind, streams of plasma ejected from the sun, and how it affects the Earth's climate system. But it's just one example. So what is space weather? The environmental conditions in space are influenced by the solar activity I mentioned before, because sun is emitting energy, and it is emitting this amount. I'm not even going to try to pronounce that. A huge, unimaginably huge amount of energy in three forms: in form of light, in form of particles, and in form of magnetic field. Just to make you imagine how huge this source of energy is that in 1 second, during a single second, the sun transforms 4 million tons of matter into pure energy. So bits of sun rotate, and they rotate at different speeds, and like I said, they're twisting the sun's magnetic field lines, and this is how they get twisted up, and the stress becomes too great, and they eventually erupt with this energy that is emitted into space. And this changes the space environment also near our planet. So this is what it looks like when we, of course, it's not what we observe normally, but these are some of the phenomena that are constant or happen from time to time between Sun and the Earth. So near Earth we have aurora, we have geomagnetic storms, and this is the magnetosphere that also protects our planet. In between we have solar radiation storms and solar wind, and there are lots of phenomena on the Sun like solar flares, coronal holes, coronal mass ejections, and so on. So this is only to show you that it's not a very steady or calm relation or system. It's constantly moving and changing, and the patterns that are caused by this are very complicated. This is just to show you that what you have here is an interplanetary magnetic field. Everything in here is like filled with interplanetary magnetic field. And if we draw how this magnetic field is formed, it is formed like this, like I don't know how to call it, like shells maybe. So this is not linear, this is not simple, this is very much complicated, but still there is a pattern. So I mentioned those events that take place on the Sun surface, and the most important and the most significant for Earth are several types, like solar flares and coronal mass ejections and geomagnetic storms that are a consequence of it. So let's start with solar flares. What are they? So the solar flares are something that is very, very hot, we might say. So they heat the solar atmosphere to a very, very high temperature, unimaginably high, like 50 million Celsius degrees, and which means that they are hotter than the surface is hotter than the Sun's core. And we recorded such event. Of course, they took place earlier, but the first historically recorded took place in September 1859, on 2nd of September, and actually, it was very quite funny that two astronomers happened to be looking at the Sun at the exactly same time and the exactly right time, so they spotted this solar flare. And solar flare looks a little bit like this. So it's like eruption of plasma into space. And if an astronaut is in space during the solar flare, they see a very specific thing, like bright streaks of light. And this means that very energetic, very high energy particles are zipping through their eyeballs. So, and those events happen all the time. For example, in 2012, in August, the 31st of August, there was a very long prominent solar flare, and solar material that was hovering in the Sun's atmosphere erupted into space exactly at 4:36 p.m. So it's a sudden event. We can record that it doesn't happen for a million years like normally in geological times, but it can be 1 second. And seen from some of the observatories, this flare caused a huge aurora on Earth. Is September the 3rd. And an average solar flare like this releases enough energy to power, for example, the whole electric system of the United States for 10,000 years. So you can imagine the amount of energy that explodes, that is ejected into the space. So this is one phenomenon, and the other one, very well known and very much observed, are coronal mass ejections, called CME. In short, you can meet this abbreviation everywhere in space weather forecast communication too. So coronal mass ejection is basically an outflow of plasma from solar corona or through solar corona. Let's come back to the how the sun is constructed. Well, we have sun corona, this layer here, this part here, and this is where the CMEs, coronal mass ejection, occur. So they are very, very large. Just average coronal mass ejection can be as big as millions of kilometers, but they are very light. So if we can compare it to a mass of a small mountain, which is not a lot compared to the size of this phenomenon. And as for record top coronal mass ejections, we had this very fast coronal mass ejection, because you remember it's an outflow of plasma, so it's huge, but it's also very, very fast. And in August 1972, this plasma traveled from the sun to the Earth in less than 15 hours. And this is very, very fast, because it means that the speed was 10 million kilometers per hour. 10 million kilometers per hour of those millions of kilometers in size plasma. So this is really, really huge. So both of those phenomena, solar flares and CMEs, coronal mass ejection, if they reach magnetic field of the Earth, our magnetosphere, they can cause a very serious disturbance. And this disturbance is called a geomagnetic storm. And this is something you may have heard about, because people are worried about it in many contexts. Not that long ago, well, probably you were not born yet, but I was. So in March 1989, on 13th of March, there was a geomagnetic storm that caused something we call blackout. It means that it was an error in all electricity systems. None of the electricity systems worked. It happened in Quebec, Canada, and it caused huge loss, huge financial loss, like £4 billion. So this is another consequence of those events, very serious financial consequences. And actually, in this case, we were not able to do anything about it. Actually, after that event of 1989, there were some other geomagnetic storms, maybe not as strong as this one, but the systems, at least in United States or in Canada, are better prepared for it. But as for the preparation and protection from space weather catastrophic events, we'll get to that later. Also, we have high-speed solar wind. What is solar wind? It's basically protons and electrons. And they flow from the sun, outward, and they're also in a state known as plasma. And during the coronal holes, the high-speed, in the areas of coronal holes, very fast, very high-speed solar winds are produced. And but the intensity or density and speed of it is not constant. For example, in 1999, in 3 days in May, this high-speed solar wind or solar wind nearly vanished. So there was no longer any proton-electron expulsion from the sun. And this also had consequences to the Earth, actually most specifically to the Earth's magnetosphere, that caused expanding its volume 100 times. So it was something that we not perceive from the Earth's surface, and luckily did not affect our lives that much. So, sorry. Yes. Well, there's we have like exciting images of it, how it looks like, high-speed solar wind looks like. And we have images provided by some spacecraft like this one, and it only highlights the importance of understanding those dramatic events, because solar winds and geomagnetic storms are actually very dramatic, catastrophic events potentially. Solar wind can generate massive geomagnetic storms. And another phenomenon that is connected with space weather and with the sun, of course, are sunspots. So sunspots are dark spots, dark regions that appear on the surface of the sun. And here they seem to be tiny, but each spot can be planet-sized, so can be as big as Earth. And why are they dark? Well, they are dark because they are cold. Well, they are not cold, but they are colder than the areas of sun around them. So there is a large sunspot, it might have about the temperature about almost 4,000 Celsius degrees, but it is cold in comparison with the rest of the surface, well, which is much lower than almost 6,000 Celsius degrees temperature of this bright sphere that surrounds the sunspot. And sunspots form on the surface of the sun, again, due to the strong magnetic field lines coming from within the sun. And these sunspots can be very big. They can become many times bigger than the Earth. And like I said, they're always dark because they're cold. And they have two parts. This inner, very dark part is called umbra. And the outer part, a little bit lighter, is called penumbra. And during the maximum activity of sun, they are very, very common. There are lots of sunspots if the solar activity is large. And the largest sunspot that we recorded, again, probably not the largest in the history of Earth or Sun, was recorded in 1947. And it was really huge because this area was as big as Earth, 330 times bigger than Earth, exactly. So, like I said, they're a common sight on the sun during the years around solar maximum. And solar maximum is the period of the greatest solar activity in the solar cycle. I'll show you the solar cycle in a minute. And so this is what they mean. When we see there are lots of sunspots, it means that the activity of the sun is quite big, quite intensive. Probably to show you. This is the surface of sun seen from satellite. What you see here, you see those spots, like this one on the right. You see they're growing, they're getting larger and larger. And inside the spot, there is this very dark spot, umbra, and around it, penumbra. And they're not constant. They're changing, they're moving, you might say, and they're growing. Okay, so this is what it looks like. Okay. So remember, sunspots are cold points on the surface of the sun, and when we see them, it means that we have a very intensive moment in solar activity. Well, so we got to the solar activity and activity cycles. So the sun has a cycle, an activity cycle, much like the hurricane season, for example, or monsoon season. We know when to expect more or less the hurricanes in certain areas. So this cycle is about 11 years long, and it has its minimum and it has its maximum. So at solar minimum, we can see no spots for many days, no spots, no sunspots. And at the maximum, there can be several hundred of sunspots on any day. Here we can see an image of sun. You can see each image is very different. This is from 1997, 1998, and 1999. This is sun approaching its maximum. And I will show it to you on the video. This is a cycle, 11-year cycle from 1996 till 2006. You can see the surface becomes more and more active. What you can see here are CMEs, coronal mass ejections, sunspots, and now almost the whole surface of the sun is covered with this activity. And in the beginning, it was calmer, we might say. Another coronal mass ejection from many different points. And there was a maximum, and it's coming back to minimum, and until the next cycle begins. Okay. And this 11-year long cycle of solar activity is often used as an argument that climate is changing because the solar activity is changing. If there is a minimum, then it's colder. When it's the maximum, it's hotter. The temperature is rising. But actually, it's not the case, because in general, the solar activity, even though there are some very large events, the solar activity is decreasing, and it has been decreasing for 10 years, while the temperature, the average temperature on Earth, was growing. So it's not that simple that when the sun is more active, then the temperature on Earth is growing. So let's go to some top events that were recorded in history. Actually, there was the biggest event ever recorded, a huge solar coronal mass ejection, CME, that hit the Earth's magnetosphere and induced one of the largest geomagnetic storms on record. So it all happened in 1859. I already mentioned this event shortly, and this is called the Carrington event. And Carrington event is also called the perfect solar superstorm. We compare everything, every event of this kind to Carrington event, to its intensity, we might say. So it all happened in September, and actually there was a astronomer, a British astronomer, Richard C. Carrington. There was actually another astronomer. I mentioned that there were two people who looked at to observe the sun at exactly the same time and spotted the same thing, but the other one was Richard Hodgson, and for some reason we call it Richard Carrington, probably because he published it first, because that's what also counts in science. You have to publish your results first, so you're remembered during the history. So imagine that Richard Carrington was observing the sun as usual, and actually at one point he saw a spot, and he drew this spot. You can see here those sunspots, darker in the inside and lighter on the outside. And he didn't, at first he didn't realize it was so important, but he saw it growing, and as a consequence there was a wave, an invisible wave that crashed into the Earth. So it was a wave of electrons, and they were caught in this giant magnetic current. And what happened on the Earth several hours after Carrington observed those spots? Well, the only infrastructure, the only electric infrastructure that was present in 19th century, which were telegraphs and telegraph circuits, they were destroyed. Actually, the people who were operators of telegraphs, they got electric shocks. Some of them died. Even when they were off the grid, they still got electric shocks. The paper in telegraph offices caught fire all of a sudden. No one knew what was going on. So even with the batteries disconnected, there was this giant stream carrying messages. It means that they disconnected the telegraphs from the grid, but still the stream was carrying the messages that were put into telegraph. Also, the lights danced in the sky. This is how it was described. So it was really a huge event, kind of an Armageddon type event. And yes, here you can see this this image drawn by Richard Carrington, and it was the largest solar storm ever recorded. So the amazing thing is, for one thing, that before all the monitoring equipment was put in place, one astronomer spotted this sunspot, this flare, before the storm reached the Earth. So people realized that there is a connection between those two events. And this is the one thing that, of course, those telegraphs were destroyed. People got electric shocks. Paper was got on fire, but also giant auroras appeared, even in areas where auroras are not normally visible, because auroras appear usually or northern lights or southern lights, so they appear around northern and southern pole. And on this day, actually on the 2nd of September, skies all over the planet like erupted, like went on fire, in red, in green, in purple. And the historical records say that newspapers could be read as easily as in a daylight during night. And everyone thought that it was the day, even though it was midnight, for example. And auroras appeared. Those skies went on fire in Cuba, Bahamas, Jamaica, Japan. So in regions that are not normally places when you can observe auroras. Actually, we were quite lucky in 2012 because there was a solar storm, geomagnetic storm of similar magnitude as this one during Carrington event, but it passed us, it missed us without striking our planet. It was missing us by 9 days. So it was really, really very, very close. So this was the biggest event of this kind. I will show you some more later. But what is the influence that space has on Earth? We already know it can hit infrastructure very hard, especially electric infrastructure. because it is a river of electrons and protons, so it may destroy everything on its way. But actually, space weather may also influence Earth's climate or even weather, but not quite in the way that you normally think that like I said, when the sun is very active, it's hotter on Earth. It's not like that. It's actually more complicated. So scientists believe that interplanetary magnetic field, called IMF, which is, the magnetic field that is pushed towards Earth by the solar wind, can cause certain effects in Earth's ionosphere, and it can cause some unexpected results, like changes in atmospheric pressure. So very close to us, we were close to the sun, and now we're in the atmosphere, so something that affects us directly. So this is called a Mansurov effect, that abnormal changes in pressure are caused by solar wind. So the sun, solar can. Sorry, I saw a question. I read somewhere that solar explosion may cause mass extinction. Confirmed. Well, as for the mass extinction, the 5 mass extinction events that the Earth faced, there are lots of theories, and for each there's actually a set of theories, like volcanoes, solar explosions, and so on and so on. It might have caused that, but except for some events that we have traces of, like the giant meteorite that killed, that initiated the extinction of dinosaurs. We have a proof, we have fossil, but in other cases we don't know. But it actually could cause mass extinction. All depends on density, on direction, on how it hits the Earth, when it hits the Earth, how strong it is, and so on and so on. So extinction would be possible, but other maybe less dramatic consequences from the point of view of the Earth, but not that less dramatic from human point of view, are also discussed by scientists. So I mentioned Mansurov effect. Actually, it was two scientists, Falgard and Mansurov, who did some research in the 60s, and they discovered that where is a changing in shape, diurnal variation in shape of magnetic field, especially in high latitudes, it may cause some strange behavior of pressure, we might say. So can cause effects in our troposphere. And another type of very direct and very close effects, maybe not so directly related to solar activity, but also to space that affects Earth, are clouds. They're called noctilucent clouds. They look like this or like this. You may have observed them. They're actually caused by meteor smoke. They're very, very strange. They were a mystery dating back to the late 19th century. So they were noticed after the eruption of giant volcano Krakatoa. So ashes from this Indonesian volcano caused splendid sunsets at evening sky, but also caused those strange clouds that remained for a long time in the sky. So this is basically a very similar phenomenon, but this time it is not caused by the ashes from volcano, but actually from meteors. And another event showing you what might happen, but actually what actually did happen. So the Carrington event affected the infrastructure the most, but the infrastructure wasn't that developed at this day. It was, remember, it was 1859, so, well, telegraphs were the only electric devices that were present at the time. But actually, later, during Vietnam War, so we are in 1972, there was another very mysterious event. So suddenly a series of American undersea mines exploded. Apparently there was no cause, it just exploded just like that. So they were thinking that maybe there was some espionage, maybe someone triggered this explosion, but there were no ships in the area to trigger them. So they were mind blown. What happened? Mines cannot blow all of a sudden and at the same time all by themselves. But actually, the official explanation, it's like a science fiction novel. There was a cloud of plasma ejected from the sun, and it compressed with Earth's magnetic field at a very specific spot, and as a result, 4,000 sea mines exploded. So this was the event of the 7th August 1972, and radiation this explosion, solar explosion produced was so powerful that it would have been harmful to astronauts, for example, if there was a moon mission at the time. Luckily, there wasn't, because they would probably be killed because of this huge wave. So we know what happened in 19th century, we know what happened in 20th century, but what would happen today if we had to face this kind of event, like Carrington event, for example? So what are the potential consequences in our world, which is, I'm sure you know, increasingly dependent on technology? You can see planes, satellites, circuits, all our systems are based on electricity, electronic systems. So in Europe, and not only Europe, in world's economy today, there are many sectors that could be affected by space weather. So space-based telecommunications, satellites, broadcasting, TV, internet, weather services, navigation, or even power distribution, terrestrial communication, especially in northern latitudes. So if the solar activity can disturb, for example, satellite navigation services like Galileo satellite. So this is affecting other activities in a dangerous way, like aviation, like road transport, like shipping, everything that depends on precise positioning, everything that depends on GPS, basically. So because this is what satellites do. So all those devices based on GPS would go crazy, and this would be very, very dangerous. This is an image of how it could look like, talk about this mass extinction. So once again, in 1859, the telegraph was about the only electric infrastructure that we had. And nowadays, it's different. We all have phones, smartphones, computers, and so on and so on. And the magnetic fields induced by those ions striking the Earth would cause, for example, would create powerful currents in any conductive material. So if you had an electronic device, it would be fried. It would be completely destroyed. Its component would be damaged, even melted in your hands. And think about what this would mean for our civilization. Every computer gone, satellites destroyed, power grid go down, communications gone. And from our perspective, it would be an Armageddon. It would be an extinction of our civilization. And is it possible to protect ourselves? Well, in a way, we can try to protect ourselves, protect our systems. First of all, we need to have those forecasts. That means we need to have those warning systems. We need to observe the trends and to be able to control and be able also to react very, very fast. So we would also need to react. How? We would have to be able to shield our infrastructure, especially critical electronic infrastructure, because if a smartphone goes down, it really doesn't matter. But if the whole electricity system of a country, of a continent goes down, well, that means huge problems. So we would need to shield, first of all, our satellites against solar flares, and they would need to be able to turn away from the sun and quickly fold their solar panels if they have them close to any exposed electronics, and this is how they would be protected. But also we need to shield our power grids and also have safety shut-offs. So if we have a warning system and we observe a growing sunspot that would probably hit us, cause coronal mass ejection and geomagnetic storm hitting us, we would have to have a switch off, for example, for the continent. Let's switch Europe off for 2 minutes to protect it, so that all the electronic devices are not fried. Of course, the cost of protecting our electronic infrastructure from this Carrington event or a bigger event would be billions of dollars. But actually, the cost of Carrington event without protection would be much greater and, like I said, catastrophic. So the military already has, the U.S. military has some protection, and because they need to protect from the electromagnetic pulse that is released, for example, during nuclear explosions. So with the soldiers or the military are having some nuclear trials, they need to protect the devices from electromagnetic pulse. So they're already doing it. And also, like I said, there was some protection for the systems after this blackout in Quebec in 1989. So it's not that it's totally neglected. Okay, I didn't want to frighten you, but actually I wanted to show you that there is a lot to think about, and there are to do and a lot to do research about. The space is huge, and even though we discovered a lot, there are still mysteries to be solved. So thank you very much.